Okay, I wanted to return to 2 points. You remember in the beginning I mentioned Durham's theorem. So we started off with the chain complex, an n chain, which is just a bunch of a linear combination of n simplices. So you take one of the simplices, you have a boundary operator, it gets you a chain of n minus 1 simplices, and so forth. And when you take the homology, you get the, let me write a C dot meaning for this whole complex. This is the simplicial homology. And you can dualize this sequence, and so then you would start with C0 on that end, and you get D star to C1, so in D star. And these are cochains, so this is the simplicial cochain complex. And you get basically the duals of these, so the same dimensional, finite dimensional vector spaces, which is simplicial cohomology, which is sort of the most elementary combinatorial cohomology theory. And then we had the Durham map, which took differential forms to cochains, because you can integrate a differential form over a chain and get a number. And the claim of Durham's theorem is the statement that that map induces an isomorphism on the cohomology groups. So the Durham cohomology, the null space of 1D divided by the boundary, the range of the previous D, the Durham cohomology is isomorphic to what you get just by doing this combinatorial thing, simplicial cohomology. It's a deep theorem because the Durham complex is a very different thing, infinite dimensional function spaces, but the null space, the homology spaces are the same. Well, we've essentially proved this without trying at this point by coming up with the finite element exterior calculus. And why is that? Well, look at the most geometric of the finite element spaces, the ones invented by Whitney, P1 minus lambda k. This has 1 degree of freedom per k-dimensional face. And namely, that degree of freedom is u goes to the integral over the face of the trace of u. And we know that if you give me, so for example, if we're talking about a 1 form in 2D, you tell me a number on this edge, and a number on this edge, and a number on this edge, I can find a unique differential form whose integral of its trace over the edge is that number. Trace being the tangential component, if we think of a vector proxy. Okay, let's think of that in a slightly different way. If we take a face, we have given a face of dimension k, there exists a degree of freedom associated to that face, and that degree of freedom, so a degree of freedom by definition is something in the dual space of the shape of the finite elements. So it would be in the dual space of P1 minus lambda k, and the degree of freedom associated with f would be dou f of u is the integral of the trace of u over f. So now I've just given a name to the degree of freedom map that associates with each face its unique degree of freedom. Now I could dualize that and get another map. F is equal to, so by the way, so dou here, now it maps faces to degrees of freedom, but I can extend it linearly, so it maps chains to degrees of freedom, because chains are just linear combinations of faces. And I can dualize it, and so F is by definition dou star, and that would map Whitney forms, P1 minus lambda k guys, into cochains. And you write out the definition, it's really essentially just the Durham map. It says, suppose you have a Whitney form U, that goes to the cochain that takes a chain and integrates U over it. So this is really just the Durham map. This thing here is the Durham map restricted to the Whitney elements. So we're just unraveling definitions. So we have this map that takes we restrict the Durand map, so it takes the Whitney elements to the cochains. But all these maps are trivial and they're all isomorphisms because there exists a unique degree of freedom for each face, and the degrees of freedom are a basis for this space. So this degree of freedom map is an isomorphism, right? The degrees of freedom, which is a basis for this dual space, are exactly in correspondence with the cochains. If I pick a face, that gives me a unique basis degree of freedom. So these are isomorphism maps. The Durand map is not an isomorphism, but when you restrict it to the Whitney forms, it is, because there's exactly one degree of freedom in the Whitney form for each face. Okay? So really all I'm saying is if you have a Whitney finite element space, it's completely determined by giving one number on each edge. In other words, it's completely determined by giving a cochain. So cochains and Whitney forms are an isomorphism to each other. That's what Whitney invented them for some way to think of cochains as differential forms. Well, now he had a subspace of differential forms that they're isomorphic to. Okay, so that means that the homology that you get using the P1 minus lambda k sequence, so P1 minus lambda 0, P1 minus lambda 1, this would be one of our finite element differential form subcomplexes. That complex is completely isomorphic to the cochain complex, C0, D star, C1, D star, etc. The complexes are isomorphic, not just their homology. They're all the finite dimensional spaces of the same dimension with an obvious isomorphism between them. So obviously, the homology of the Whitney complex is equal to the homology of the cochain complex, because the two complexes are isomorphic. So these are isomorphic. But this is simplicial cohomology. So the cohomology of this finite element subcomplex, the Whitney form subcomplex, is just a simplicial cohomology. But then we proved that all our finite element differential form subcomplexes give the same homology as the whole Durand complex. So we already proved the hard part, which is that this is the same as the homology you get using the full H lambda k spaces. And there, putting these together, we have Durand's theorem. The Durand cohomology used based on partial differential operators on infinite dimensional spaces is the same as the simplicial cohomology based on cochains. Now, somebody might say, well, actually you only proved it for H sufficiently small for fine meshes. You can actually get away from that because it's very easy to show that the simplicial cohomology doesn't depend on the mesh. If you refine the mesh, it doesn't change. That's just a combinatorial thing. So if you have two meshes, you can find some fine enough refinement, or just keep refining until its H is sufficiently small. If you start with an initial mesh, keep refining until H is sufficiently small, then these will be equal, but this one won't have changed. So it's equal for all H. Any questions? Yeah. Well, the weak approximation issue, that's not a problem at all with these concrete spaces, because now our spaces are piecewise polynomials of degree R. They approximate any, so we know that the spaces of piecewise polynomials of degree R, if we take the union with finer and finer meshes, is dense in L2. So they approximate anything, not just harmonic forms. What do you mean if you miss the holes? The first mesh has to be a subcomplex. That's what it has to be, subcomplex. So if it's a subcomplex, it's a bunch of differential forms on that domain without holes. With holes, I mean, it has holes. So you... How do you guarantee? So I'm assuming that my domain omega, a lot of times I draw this, But that's not it. I'm assuming my domain omega has a triangulation. I'm not making any allowances for approximating the domain omega. I have to have a triangulation of my domain that respects the holes. If we wanted to go further, if we started with a smooth domain and then we were going to approximate it by something with flat holes, then we would have to check that we haven't screwed something up here. But if my domain omega is triangulated by a triangulation, then even on the coarsest mesh, it'll have the right homology. Because even the coarsest triangulation of a simplicial complex gives you the right simplicial homology. Right? If you just do a super coarse triangulation of this thing, I know something like this, and you compute the homology, you will get, there's a hole in here, you will get the right answer, even on that super coarse triangulation. It won't change when you go up to the cohomology. I'll make one further point on this line. Not only are these guys, the P1 minus guys, give the right homology, independent of whether H is sufficiently small or not, all the other ones do too. And that's because, remember, one direction is easy. As soon as we have a map that goes down, like our bounded projections, as soon as we have a chain map going down to our finite element spaces, then we get a surjection on homology for free, as long as there's a projection map. So there's never any problem showing the homology groups are less than or equal to. They're an image of the true homology groups. They might get too small, but they can't get too big if you have a projection. Okay? Now, if I take any one of our finite element spaces, let's say I take P2, lambda 0, or P2 minus lambda 0 goes to P2 minus lambda 1 goes to this, then that's a bigger space than P1 minus lambda 0 and P1 minus lambda 1. So if I take a projection down, it can be either my bounded projection or even the standard projection, because everything's bounded in a finite dimensional space. Take this projection going down, that's onto this complex. So homology is a surjection. So the homology down here cannot be bigger, it cannot have higher dimension than the homology up here. It could have lower dimension. But we know this homology is the same as if we had the whole de Rham sequence. We just commented on that. So this one is the biggest. This one is stuck in between them because it's less than this, but it's more than this, and these two are equal, so this one is equal also. So actually, you take any of our finite element de Rham subcomplexes on any mesh, no matter how crude, it will capture the homology exactly.
I have two quick questions. First is, can you explain when this proof was originally given?
This proof?
Is this a new proof?
This proof was originally given, I think it's 4 minutes ago I started.
This is not the original proof.
So actually, this is quite amazing. So there are variations on this proof that I've been thinking about that you could. So there are several reasons why this is not what everybody calls de Rham's theorem. So there's that issue. And I need to talk to topologists to think how serious they would consider that. First of all, we're defining the homology at the continuous level by the H lambda k's, not by the C infinity lambda k's. L2 cohomology, not C infinity cohomology. Does that make any difference? No, basically because of elliptic regularity. If you have a harmonic form, it's C infinity. That's in the literature in various places, but it's not something that you see in a textbook. So that's issue one. Two is most statements of de Rham's theorem in textbooks don't talk about the simplicial cohomology because they don't want to restrict themselves to domains that have a triangulation. So they use what's called singular cohomology, where, well, I don't know, that is in the the beginning of every topology book. There's another thing that you can define in any topological space that generalizes this simplicial cohomology. And very early in most textbooks, they prove if you have a triangulation, simplicial cohomology is the same as singular cohomology. So that's a sort of elementary theorem. But And then there's another theorem that says every manifold has a triangulation. So then you put those together, and then you can say that we've proved de Rham's theorem on manifolds, which is where it's normally proven. Now then the other aspect of it is I showed they have the same homology, but I didn't show the de Rham map is inducing that homology. I showed our bounded cochain projections are inducing it. I can fix that, but that's another little issue. So actually I've been trying to decide if maybe I should do something with this. Maybe it should be in American Math Monthly or someplace like that. I don't know. But now the ingredients to give the proof, even with those extra variations, they're in Whitney's book. And Whitney's book also has a major chapter on proving de Rham's theorem. So when I was finally able to understand that part of Whitney's book, I was amazed to see this was not the proof or anything like it. He gave a very different proof that I would regard as more complicated, even though he invented all the ingredients that you need to give this proof. Now, one thing he didn't know, as far as I know, although he knew an amazing number of things, but one thing that I doubt he knew is that there exist bounded cochain projections. Well, if one's a refinement to the other, it's easy to see it. So, this is easy to do, actually. This was a homework exercise that my roommate had in his, one of the few math courses he took. Take a triangulation and add one additional triangle to it. Cut one triangle, do some simple kind of refinement of a triangle. Cut two in half like this or something like this. And then just do the combinatorial calculation. What happens to the matrices? That's it, basically. Marcus? Does orientation matter for this? I might be wrong. Now, I'm really very far from being a topologist. I don't think that orientation is an hypothesis for this. I think that if you have a Mobius strip and you cut a hole in it, you can use homology to find out there's a hole in your Mobius strip. I might be wrong. That would be my guess. We have anybody who knows really knows topology? How do you have torsion if we have real cohomology? There's no torsion. What?
You won't pick up the fact that it's twisted if it's a Mobius strip because it's real cohomology.
Right, I don't want it, but I'll still find the holes, right?
But you'll see the hole.
Yeah. Okay, anything else? Now I wanted to go back to one other point that we had discussed. There was this funny business where I said that when Dojuk and Patodi managed through great labor to prove convergence of the eigenvalues for what we later see as a mixed method, but they didn't think of it that way, their big problem was that they couldn't show that this operator is consistent. And I want to say exactly what that means because it's still, as far as I know, an open question. In some sense, we don't care about it because we use the mixed method and the issue doesn't arise. But it's still an interesting question. If you did take that point of view, is it a consistent operator? So I'm going to turn it into our notation and way of thinking about it. We have, if you take a smooth differential K form, then we can associate it to a Whitney form, as we just discussed. So this is sort of our capital pi h. And this is the thing so that pi h of u has the same integral of the trace over every k-dimensional face as u does. For all f in delta k. Okay? So that's a nice operator that we understand very well. We're not 100% happy with it because it's only defined on things that are at least continuous, but it's nice commuting projection. Now we have the D operator that takes P1 minus lambda k to P1 minus lambda k plus 1. And so we have a D star H operator. I put the H on here because this is dependent on what spaces you put here. All these depend on the mesh TH. And this one goes from P1 minus lambda K. Actually, let's do K minus 1 and K here. So this will go from K to K minus 1. And the formula is D star H of some K form. That's a K minus 1 form whose L2 inner product with P1 minus lambda K minus 1 is the same as the L2 inner product of U with D tau. That's how D star H is defined, which unfortunately is a global operator because you have to invert this mass matrix defining this thing. Okay, so now we can take any U and we can pi H it into the lowest degree order Whitney space, and then we can take D star H of it, and that gives us a differential form, a P1 minus differential form of order K minus 1, and we could compare that to the true D star U. And we could ask whether the limit of H goes to 0 as the mesh is refined of that is equal to 0. And, okay, it's an open problem and it's been conjectured in both directions. So Dozuk and Patodi gave a wrong counterexample. So they thought they had a counter. So first they tried to prove it, I'm sure, for a long time, and then they gave what they thought was a counterexample. But a guy named Smits, and this is much more recently, this is the mid-70s, and this is the 90s. A guy named Smits showed the counterexample was not a counterexample, and proved the positive result for 2D manifolds, 2D Riemannian manifolds under uniform refinement of the triangulations. And he conjectured it's true in higher dimensions, but didn't succeed in proving it. And that's where it stands as far as I know. Yeah?
So why do you need the cochain projection there? Because the DH star is perfectly well defined whether U is in the finite element space or not.
Well, it's not DH star anymore. If we consider to be DH is D restricted to P1 minus lambda K minus 1, then that operator has an adjoint, and it's this. And it only acts on, I mean, if we're thinking of this as being the operator inside our discrete complex, right? We have our complex, P1 minus complex. Now, from their point of view, it's totally natural to consider this, and that's why this kind of thing is more important for them, because they think of, at least Dozuk and Patodi, and I don't know what Smits is thinking, they are using these Whitney forms as a tool. They really think the cochain complex is the key guy. And they're trying to prove things about this cochain complex. And they're going to say, well, how are we going to define a D star back? So this is D star, this is D. How are we going to, so this is their discrete D. They would call it a DH, although they don't use H for discretization. They say there's the continuous world where topology lives, and then there are cochains, which is discrete topology, and has a discrete D, and then they say, oh, to do the Hodge-Laplacian, we need a discrete D star H. And how the hell are we going to find that? Oh, I got an idea. These things are the same as Whitney forms, and Whitney forms, so in our notation, P1 minus, they have, well, these are differential, well, so Whitney forms have an inner product on them and stuff like that, so I can take the adjoint. I can't really take the adjoint to this because I don't have a natural inner product on cochains and things. So I'll use the inner product up here to take the adjoint of this operator and define this. And that's this operator I wrote down in our notation, D star H of pi H. What's that? Yeah, somewhere. Drop me an email. It's in the Israeli Journal of Mathematics, and there might be a reference in our bulletin paper, but drop me an email. I have it. I have a copy of the paper.
So why do you put the cochain projection there, not the L2 projection?
so that you can't just mail a paper in right away. The L2 projection, it's obviously true, I think. But this was the question. Because this is their connection. In their connection, they don't have bounded cochain projections, and they don't have L2 because they... It's sort of funny. They don't think of these spaces as having a natural metric or a natural product or things like that. They think of the Whitney forms as some sort of funny tool by which they can work with these spaces. So to define D star H, all they did was use this L2 inner product up here as a way to define this. But they didn't... So in my opinion, if you want to analyze this operator, which is, if you want to analyze this approximation, which is DHU, DHV plus D star HU, D star HV equals FV, you shouldn't look at it in this way. That's all the wrong way, and it's going to be very hard because you've got this operator that's not even obviously consistent. You should look at it in our way, right? It is a mixed system, do everything in L2, then it becomes relatively easy to do it. And when I spoke with Dodzuk, he said, yeah, that's great. We would have loved that if we had known something like that existed. Yeah? I'm not sure what he wrote in his paper. And I must admit, I have not read his proof to see that it goes through, but it looked awfully computational. You know, you take a refinement, you could write down matrices and things like this. Okay. Any other questions? Okay, so I have 3 final topics to do today, and I think I'll make it. Maybe even end early on the last lecture, but probably not. So we keep coming back to these bounded cochain projections, and I keep saying, well, you can do them, but I haven't I haven't really said anything about them, and I'm not going to go through it in detail. The references for this, since I'm not going to go through in detail, well, there's a pretty good job of it done in our ACTA paper, which is the first place it was all written out in one place, and maybe the first place where the construction was all in one place. As I've mentioned a couple of times, and I'll mention in the slides, the key ingredients were not invented by us and not done in that paper. They're invented by Schoberl and Christensen. But there's also a paper of Christensen and Winter that came a little bit after, both to make it apply more generally and maybe to clarify things a little bit. And there's still a lot of open work, a lot of work going on in this area, especially for the P method. And as I mentioned before, a sort of open question is to get this all to work well for elasticity complex. So the degrees of freedom defining any of our de Rham subcomplexes give you canonical projection operators. Given a continuous differential form, take the one that's in PR lambda k, such that all those integrals that are its degrees of freedom have the same value. But that's not a bounded operator. Well, you need it to be continuous or something so that you know you can integrate its traces. So it's not bounded even for 1h, much less uniformly bounded. And again, this is nothing surprising. The piecewise linear interpolant, which is the case of zero forms, is not defined on all of H1, even for one triangulation. So then Christensen said, well, why don't we apply a smoothing operator first? And now I'm following the approach of Christensen and Winter, which generalizes things a little bit. They define a smoothing operator with 2 parameters, and it should at least take L2 differential forms into continuous differential forms. In fact, it'll take L2 differential forms into C infinity differential forms. And it has to commute with D. So first of all, you have to find a smoother that commutes with D. And then you define this Q epsilon H to be, first you smooth by R epsilon H, and then you take the regular projection based on the degrees of freedom, since now these guys are continuous, so that makes sense. Now you have an operator that's defined on all of L2 lambda k. And since the pi commutes with D, and since we assume that R commutes with D, Q commutes with D. So now we have a map from L2 differential forms into our finite elements, which commutes with D. But it won't be a projection. The main thing we wanted was a bounded commuting projection. So we got bounded at the cost of losing being a projection. So that's where Schoberl's trick came in. Schoberl said, well, take this Q epsilon H and restrict it to the subspace. So that's not the identity operator. It'll take something in the subspace to something else in the subspace. If it were the projection, it would be the identity, but it's not a projection anymore. But we're cooking all this up so that the smoothing operator is very close to the identity, so this Q is very close to the identity. So at least for H sufficiently small, this at least should be invertible. It's not the identity, but it's close to the identity, so it should be invertible. So we can take its inverse and compose that with Q itself. Now, since Q commuted with D, its inverse commutes with D, so this new guy still commutes with D. But now if you start in the subspace, you apply Q, and then you apply the inverse of Q on the subspace, you get the identity. So now it's a projection again. I think that's very clever. That's Schoberl's trick. Okay, so now we have to show that works. We have to show how you would pick the smoothing operator in order that you can prove that this operator not only is defined, so we have to show the Q really is invertible, but not only is it defined, but we have bounds uniform on H. And that's a bit messy. Nobody does it in less than a couple of pages. So the way I've presented it here is first let's ask what properties we need of R and Q, and then let's see if we can come up with the operators that get them. And it turns out that there are two analytic properties you need of Q, which is pi h r epsilon h. One is we have this free parameter epsilon. I haven't said what it's for. We're going to use it in actuality to get the property that Q epsilon h, actually it'll be used in the second one. So for now, for each epsilon, we have to make sure that Q epsilon h is uniformly bounded. So that means for all positive epsilon, maybe small, there's some constant, but it's allowed to depend on epsilon, such that the norm of Q epsilon h as an operator from L2 to L2 is bounded. Okay, as epsilon goes to 0, your smoother is going to be going to the identity, so then you couldn't have it bounded. But for fixed epsilon, you could have this uniformly bounded. That's one property that we'll need to establish. And the other property is that the Q epsilon's h's converge to the identity, and here's where we make use of the other parameter. Fix the h, let the Q epsilon h's, let the epsilon go to 0, the Q epsilon h's go to the identity, and that should happen uniformly in H. Okay, these are the things that take a couple of pages in applications to prove, 3/4 of a page each or something, but suppose these hold, then you define pi h by Schoberl's trick, Q epsilon h restricted to the thing. Because of this condition here, for h sufficiently small, pi h is well defined. As soon as this norm is less than 1, you can use a Neumann series to invert Q epsilon h. So pi h is well defined, and therefore for h sufficiently small, pi h is a cochain projection operator. And you can prove these bounds. And these bounds are as nice as you could want because they're optimal order, CH to the S, omega and HS norm, S up to the largest allowable by the spaces, R plus 1. But also S can be as small as 0, which just says pi h is a bounded operator. So it applies to as rough elements, as rough functions as you want, just L2. And for smooth functions, it's optimal order. Okay, now just a word about how you define R epsilon h. The easiest choice is sort of a straightforward mollifier. So what's a straightforward mollifier? You you take a function like this, which is, say, supported in the unit ball, and has integral 1, the usual thing we do, and basically you take rho convolved with u, so that really comes down to the integral of rho of y u of x plus y. That smooths things, but you want to do this also with, you want to do this thinner and thinner, so you might put an epsilon y here, and then there's a power of epsilon here or something like that. That's the usual convolution, rho sub epsilon convolved with u, where rho sub epsilon is the scaled rho, epsilon minus n rho of epsilon inverse x, right? So that's the usual smoothing operator, dy over b1. So it's just saying we're going to take averages of u, and u shifted around by a little distance epsilon in all the ball. Now in our cases, we're going to use epsilon sub h. And also, to make this work for all differential forms and make it obvious that it commutes with d, I'm going to think of this as a pullback. I'm going to think of this as f star epsilon h of u, where f epsilon h, fy star. So it depends on y, and it depends on epsilon h. Fy epsilon h of x is x plus epsilon hy, that translation. So another way I'm saying it, right, pullback for zero forms is just composed with the map. So I'm saying I'm going to average u and translations of u in translating at a distance less than or equal to epsilon h, and average over all of those. Okay, so that last way of writing it goes over immediately to differential forms. So r epsilon h of u is the integral over the y's in the ball of our weighting function, which rho, times the pullback by the translation operator, where you translate epsilon hy distance u. This way of writing it came from the Christensen and Winter paper, and one reason it's very nice, it affords a lot of flexibility. Here I've been talking about 1h, so it must mean I have a quasi-uniform mesh. All the elements are roughly size h to get these estimates. But they said, no, you don't need that, because you can pull back by anything here, so you could make it epsilon h of xy. It's still an average of pullbacks, so all pullbacks commute with the d operator. Then there's one other technical issue, and this is the issue that comes up with the elasticity sequence that's causing a headache. And that's when you mollify and you do a little translation, well, if your domain's over here, if you get very close to the boundary, your mollification region will pull you out of the boundary. So there are two approaches to dealing with that. One is you first define an extension operator. So you define r epsilon h of u is equal to this mollifier. Let's call this m epsilon h of u. And you apply m epsilon h to an extension of u, where E maps h lambda k, or L2 lambda k of omega, to L2 lambda k of a slightly bigger domain. Of course, the extension operator has to commute with d. And so that means the extension operator is probably going to be defined by a pullback. And the way you do that is you take your slightly bigger domain and you figure out some sort of mapping from the bigger domain into the smaller domain. There's various ways to do that. And the extension is the pullback of that mapping. The other way to do it, which Schoberl and Christensen pointed out, is what I said here is that every point we're going to average over its translations in a little ball around that point. The ball doesn't have to be around the point. The ball could be towards the edge of the point. Actually, the ball could be outside the point as long as it stays within a distance epsilon h. So you could make the ball you take depend on the point, and as you get close to the boundary, you make sure it's on this side of the boundary, and then in the middle it would be pretty much. It's possible to do that. And then it's possible to modify it for Dirichlet boundary conditions and stuff like that. Okay, and then, of course, with this definition, you have to prove these two key guys. And basically, it's scaling and macro elements, and making use of that epsilon, but that's where it gets technical. Any questions? Okay, I had many requests to talk about bases for these spaces. And what I'm going to talk about is in a paper that was joint with Rick and Ragnar and was published in Computer Methods in Applied Mechanics and Engineering in 2009, before I signed the Elsevier boycott. But it's not our most readable paper. I found, as I was reviewing it yesterday, it's somehow a complicated business. I'll try to give you an idea of it here. So we already talked yesterday a little bit about, and by the way, in doing so, I'll get to a lot of subject that precedes this, like the Whitney's fundamental forms and so forth, and those are very nice, and they're good that we get to a reason to talk about it. So I already talked a little about the Bernstein basis. Let's talk a bit about that. So, right, we have these finite element spaces, lambda kh, and we have the degrees of freedom. U goes to the integral over f of the trace of u times some q for q in some space. That gives us a basis for these spaces, because this is a basis for the dual space, and we have the dual basis, which is then a basis for the regular space. Namely, the basis elements would be the one for which one of these degrees of freedom equals 1, and all the other ones equal 0. So as a very simple idea, suppose we take cubic P3, so 0 forms, in one dimension, and as our basis is just, say, the value at these 4 points. Do a nodal basis rather than integrals in the interior. So then, I tried to draw this picture the other day and did a pretty crummy job. There's one that's equal to 1 here, and 0 at the others. And so those are these guys. So there's the blue one, which is 1 at the first node and 0 at the next 3 nodes. The red one, which is 1 at the second node and 0 at the other 3 nodes, and so forth, the yellow and the green. So that dual basis exists, and that exists for any finite element space because degrees of freedom are part of the definition of a finite element space. And the way you compute those is, well, that would be well, here you could use simple calculus, but you could also just write down a 4x4 matrix. Take any basis of P3, like 1x, x squared, x cubed, evaluate the degrees of freedom on it. That gives you a 4x4 matrix, and inverting that matrix, you get these guys. That's the columns. If we're going to use one of these fancier spaces, it'll be a big matrix. We'll have to compute it. You don't have to compute it each on each element. You compute it once on one element, and then you move it around with the pullback operation. But there's an alternative to that, and that's an explicit basis that you can write down, and it has some nice properties. It has really wonderful properties for some aspects of approximation theory and design, and much preferred there, but it has some advantages also for finite element analysis. And so the Bernstein basis is given in terms of the barycentric coordinates. And all it is if you have, well, in 1D, you have two barycentric coordinate functions, lambda 1, lambda 0, which is 1 at 0 and 0 at 1, and lambda 1 here. And now you take the lambda 0 to the I, lambda 1 to the r minus I, and that's an element of PR. And those are the Bernstein guys. And those are shown here. So this is lambda 1 cubed, and this lambda 0 cubed, and this is lambda 0 squared lambda 1, and lambda 0 lambda 1 squared, and lambda 1 cubed. And that also is easy. Well, these obviously span P3, so that gives us another basis. Okay, and so the purpose of this paper was to figure out what is the Bernstein basis for the PR minus lambda k and the PR lambda k families. And two cases were clearly known. So for PR lambda 0, which is just the PR Lagrange spaces. That's the usual Bernstein basis. I'll show you the picture in 2 dimensions on the next slide. And an interesting point, which we already saw, is that if you go down to the case of P1 Lagrange, this is equal to the dual basis. So the Bernstein basis for P1s is just lambda 0, lambda 1, and the barycentric coordinates for P1s are just lambda 0 and lambda 1. They're the same thing. So for P1 minus lambda 0, it's going to turn out that the analog of the Lagrange basis is the dual basis. So what we would say is a Bernstein-like basis and these elements, these are going to be called phis of something. Those elements, those are the basic Whitney forms, which I'll have to define, which Whitney defined first. In fact, Whitney didn't define a space, didn't use the Kazul operator. He defined these basic forms, and the space was just the span of those forms. What? Lambda k, that's right. Thank you, that's important. Okay? So we have to do some preliminary computations with barycentric coordinates, and as I say, I'm delighted we have a chance to do them. By the way, here's a barycentric coordinate in 2 dimensions. Okay, so on an n-dimensional simplex, there are n plus 1 barycentric coordinates, lambda 0 through lambda n, 1 for each vertice. So the sub-0 refers to the vertex x sub-0. And they form the dual basis for P1 functions, dual to evaluation of functionals at the vertices. And P1 is, of course, the same as P1 minus lambda 0. Okay, so here's a computation. Suppose we take all but the first of those barycentric coordinates, d lambda 1 through d lambda n, and we wedge them together. Why don't I wedge all of them together? It would be an n plus 1 form, and there aren't too many of those. So this way I get an n form. How many n forms are there at every point? They're all multiples of the determinant. And this is a constant n form because lambda 1 is linear, d lambda 1 is a constant. So this is just a multiple of the determinant everywhere. It's a constant n form. It's an element of alt n. So it just must be a multiple of the volume. It has to be. There must be a number c such that this guy is equal to c vol. How do you figure out what that constant c is? Well, you could just evaluate it on any set of n vectors that doesn't give you 0, and the ratio will be that constant c. So let's take a picture in 2 dimensions. We have the 0 vertex, the 1 vertex, the 2 vertex. Then we can think of x1 minus x0 as a vector pointing from x0 to x1, and x2 minus x0 as a vector pointing to x0 to x2. And it's easy to compute vol of x1 minus x0, x2 minus x0 through xn minus x0. Vol acts on n vectors, and it's easy to, if it's these vectors. Why? Because that's what the volume is. The determinant of those things is the area of this parallelogram, right? So this is twice the area of the triangle. What is it in 3D? This is in 2D. What is it in 3D? What is it? Say it. 6 times the area of the parallel pipette determined by these edges. And what is it in ND? 2, 6, n factorial. The parallel pipette In ND, you can cut into n factorial simplices, easy to see. So the volume form applied to these guys is just n factorial t. Now, can we compute d lambda 1 wedge, d lambda 2 wedge, d lambda n applied to those same guys? Well, that means we have to apply the d lambda I to the xj minus x zeros. And actually, we do all of them and take the determinant is what we got to do. Okay, what is d lambda I applied to any vector? Well, maybe I should just leave. Okay, let's do this. Instead of lambda I, which is a linear polynomial, let's subtract off the constant term. So then it's a homogeneous linear polynomial. But that's a constant, so the d is the same. Okay, now this thing is nothing other than the gradient of this. Maybe I didn't have to subtract off. So this is the gradient of lambda I minus lambda 0, which is the gradient of lambda I dotted with v. So what does that mean? This is well, that's it. So it's the gradient of lambda I dot. So I want this to come out to be lambda I of xj minus lambda I of x0. Yeah. So I'm. So is this obvious? Hopefully. This is embarrassing. So, okay, what are we talking about here? Take a linear polynomial and yeah, so the so this is lambda I. Yeah, that's a better way to write it. Sorry. So I claim this is lambda I, the gradient of lambda I dotted with v that's it. So, and the gradient of lambda I dotted with v, this should be lambda I of v minus lambda I of 0. There you go. So if lambda had no constant term, the gradient of lambda I dotted with a vector v, the directional derivative of a linear guy, would just be the value on the vertex. But there is a constant term, so I should have written it this way from the beginning. A linear polynomial lambda I of v at any point v in the plane is lambda I of 0. Taylor's theorem applied to linear polynomials plus the gradient of lambda I dot v. Okay, there you go. That's true for any linear polynomial. So gradient of lambda I dot v is lambda I v minus lambda I 0. Okay, so I apply that over here and I get this. Because the 2 minus lambda zeros cancel out. Okay, sorry. So, and now what is this though? We go to our triangle here. So if this is, say, the ith node, and this is the jth node, and so if I is not, so, and then here's the 0 node. If I is not equal to j, then lambda I is 0 along this edge, so both of these guys are 0. So this equals 0 if I is not equal to j. And if I is equal to j, then this one is 1 and this is 0. So this is equal to 0 or 1. So this is, so the matrix whose determinant I have to take is the identity matrix. Okay. So this quantity is equal to 1. And so that all leads to, we take the ratio of those two quantities, that's the C I have to put here. And so that now we've done the calculation. The wedge of d lambda 1 through d lambda n, all the d lambdas, but you throw away the first one, the 0 one, is 1 over n factorial t, volume of t, times the volume form. Of course, you didn't have to throw away the 0 one. You could have thrown away the first one or the second one or the third one. You get the same formula with a negative 1 to the I. Okay. One more little calculation. Kappa d of lambda I. So here, let's see if I can do this a little bit cleaner. So kappa d of lambda I, this time I think I do definitely want to subtract off the constant term. So it's the same as kappa d of this. And now I wanted to subtract off the constant term because this is a homogeneous degree 1 0 form. And then we have the homotopy relation, because this is the same as kappa d plus d kappa, because we're at the end of the sequence of lambda minus lambda 0, lambda of 0. And the homotopy relation, well, the sum of 1 and 0 is 1, so this is just lambda 1 minus lambda I minus lambda I of 0. So we use the homotopy relation there, or compute it from first principles. So I've done two little calculations, one on the wedges of the d's of all the barycentric coordinates, the next on kappa d of a barycentric coordinate, and now I want to take kappa of the wedges, not of necessarily all the barycentric coordinates, any collection of them. So take points, indices sigma 0 less than sigma 1 less than up to sigma k, so k plus 1 guys. And so this is associated with some face, because if we took the corresponding vertices, x sigma 0 through x sigma k, that would be a face of dimension k. Okay, and I take all the barycentric coordinates belonging to points on that face, vertices of that face. I take their d's, I wedge them together, and take kappa of that. So then it's just the Leibniz rule, so I put kappa onto the first one and leave all the other ones alone, but kappa on the first one gives me back kappa d lambda sigma 0 is just lambda sigma 0 minus a constant. I'm throwing all the constants into a garbage term at the end, so this is a constant 0 form that I don't really care about. So I get lambda sigma I, and then d, the wedge of all the other d's, with a plus or minus 1 for the I. So we have this formula here for kappa times the wedge of the d's associated to a face. Okay, that green thing in there, that's the definition of the Whitney form. So it's on the next slide. We have a face F. Its vertices are x sigma 0, x sigma k. Then we define phi sub f to be that alternating sum. You take the wedge of all the d lambdas on the face. Well, that would be too many of them. That would be a k plus 1 form, and on the face it would give you a trace of 0, as you said. But you leave one of them out, and you multiply it by lambda sigma I. So it sort of looks like Kazul. You erase one of the d's, but these are not the xi's, they're the lambda i's. So it's sort of a barycentric Kazul, alternating sum. So bring it down to Earth. If we have a face which is just a vertex, so there's only one of these, well, then there are no d's left, and there's only one of these, and so the Whitney forms are the same as the barycentric coordinates for vertices. If we have an edge, then it has two indices, xi and xj, two vertices, xi and xj, and this tells us it's lambda I d lambda j minus lambda j d lambda I. If we have a triangle, then it's lambda I d lambda j wedge d lambda k minus, this time you pull the lambda j out, lambda j d lambda I wedge d lambda k plus lambda k d lambda I wedge d lambda j. So it's a very simple formula. This is the formula that's in Whitney's book. So then when we looked at this, we said, well, that's a different way of looking at P1 minus spaces and Ravier-Thomas as the span of those things. It doesn't look very much like our definition in terms of P0 plus Kazul of P0. It was used in the finite element literature as a basis. Some people knew this. I worked with these things for a long time before I knew this. How do we even know that this function is a P0 plus the Kazul of a P0? Well, the way I derived it, it's right here. That function, green function here, is a Kazul of something, which is a Kazul of a constant form plus a constant form. So it is in the subspace. Okay, and now the key property it has, which Whitney proved, and which he used, and which is sort of the basis of the Whitney forms and all that stuff of Dodzik and Patodi and so forth, is if you take a k-dimensional face and you form the Whitney form phi f associated with that face, and then you take another k-dimensional face g, if it's not the same face, if you integrate the trace of the Whitney form over g, you get 0. And if you integrate the trace of the Whitney form over f itself, you don't get 0. You get some other number, which is 1 over k factorial, but of course you can normalize it to be 1. So what that says is that this is indeed the dual basis to these degrees of freedom, integrate over the faces. The Whitney forms are the dual basis for the natural degrees of freedom of P1 minus lambda k. Now let's do that calculation there to see that you get that. That's not a hard one. So, I don't know, maybe draw the picture in 3D for a change. x0, x1, x2, and x3. Let's say we have the Whitney form. This will be our f, x1, x2. I won't always write the x's, as you see. And then we pick one of these other sides as g. It could either be 0, 3 with no points in common, or let's say it's 0, 1 with 1 point in common. Okay, and what's phi f? That's lambda 1 d lambda 2 minus lambda 2 d lambda 1. Now, x2 is not in G. There has to be one vertex that's not in G if f is not equal to G. In this case, it's x2. Okay? That means lambda 2 is identically 0 on G. Because lambda 2 is 1 here and 0 on the whole opposite face, so lambda 2 is 0 on G. But if lambda 2 is 0 on G, d lambda 2 is 0 on G. Lambda 2 equals 0 on G, and d lambda 2 equals 0 on G, because lambda 2 is 0 on this whole face. Therefore, both of these things are 0 on G, so the integral of, so phi f restricted to G is 0. The trace of, not only the integral is 0, but the integrand trace G of phi f is 0. Okay, and what about the other case? Well, that's sort of a computation, I think that we were, well, let's do it. What would be, yeah, that's one of the computations that we did, but let's write it down. So it might be easiest to do it for k forms. So we write down the whole definition of the green formula there. Instead of calling them sigma 0 through sigma k, let's just call them 0 through k. Let's say it's the first k plus 1 vertices. So this would be lambda I d lambda 0, but then you leave out d lambda I, and you have d lambda k. So this is phi f, because I'm making the simplifying assumption that phi is f is the face with side 0, with vertices index 0 through k. And now we want to consider the trace on F of this guy. That's a guy who's defined over the whole triangle. We want to consider its trace on F. Well, so that's the sum over negative 1 to the I, lambda I, the trace of this differential form on F. So if you take the trace of a barycentric coordinate, if you take a barycentric coordinate function that's defined on this whole tetrahedron, like the thing that's 1 here and 0 on this face, then on the edge it's the one-dimensional barycentric coordinate that's 1 here, linear, and 0 on the other edge. So these are just all the barycentric coordinates of F. D of all the barycentric coordinates of F wedged together, leaving out 1. Okay, that was the first computation we did. If you wedge together all the barycentric coordinates except for 1, you get plus or minus the volume form. That's the first calculation, second dot there. That d lambda 1 through d lambda n is just that multiple of the volume form. 1 over the dimension factorial. Now the dimension is 1 over k factorial, because it's a k form, times the volume form on the face F. And there's a negative 1 to the I here. We always love it when we have two negative 1s to the i's coming together. So this becomes the sum of lambda I, and I can pull this out. So 1 over k factorial times the volume form of F. And on the face F, the sum of the barycentric coordinates on F is 1. So it's 1 over k factorial times the volume form on F. And so if you integrate the trace of F, phi of F over F, you're integrating the volume form over F. And so you get with the 1 over k factorial, so you get the volume of F over k factorial. No, the integral of the volume form over F is 1. No, sorry, it's the volume of F. But here I should have had a volume of F. This is just the integral over F of dx1, dx2 through dxk, so it's the volume of F. Those cancel, and it's 1 over k factorial. Okay, so now we have that these Whitney forms are indeed the dual basis. So we have the dual basis very explicitly. It's just the Whitney forms for each of the faces of dimension k. Any questions where we are now? Okay, now I want to generalize that to all the PR minus lambda k spaces, not just the P1 minus lambda k spaces, which are the Whitney forms for which the work has already been done by Whitney. So here's a picture of the Bernstein basis for a triangle for P4 on a triangle. So those functions that are plotted there are the functions lambda 0 to the I, lambda 1 to the j, lambda 2 to the k, where I plus j plus k equals, in this case, 4. R, which is equal to 4. Okay, where did I plot them on the triangle? Well, you see, one of them only involves lambda 0 to the 4th. I associate this with the vertex x0, and I plotted it. So those are the pink ones. Lambda 0 to the 4th, lambda 1 to the 4th, and lambda 2 to the 4th. Then there's a bunch of them that only involve lambda 0 and lambda 1, like lambda 0 to the 3rd, lambda 1, lambda 0 squared, lambda 1 squared, and lambda 0, lambda 2 squared. I associate those to the edge x0, x1. And in fact, I list them there, and since this one, this is square. No, sorry, wait. What am I doing? 3, 2, 2, 1, 3. So, and I put this one closer to lambda 0 because it's lambda 0 x0, and I put this one closer to x1 because it's x1 cubed. And you get those three functions. And they're all the same color because they're all associated with that edge. But they're really different than these ones, but I don't want to use that many colors. So each edge, there are three functions associated. Each vertex has one function associated, and the interior has the three functions, which are this, where none of the ij and k vanish. So lambda 0 squared, lambda 1, lambda 2, lambda 0, lambda 1 squared, lambda 2, and lambda 0, lambda 1, lambda 2 squared. Those are the three that are plotted in the center in blue. So what is this structure? Let's look at it a little bit more carefully. The whole space of polynomials of degree r are the span of these monomials. I write it as lambda with a multi-index alpha, meaning lambda 0 to the alpha 0 through lambda n to the alpha n, where the monomial where the multi-index has degree r. I can partition these into spaces PR, TF, where the f goes over the faces. Namely, the ones, if the support of the alpha, the index set for which alpha I is not 0, if that's sigma 0 through sigma k, I associate this with the face f with vertices x sigma 0 through x sigma k. So the span of this one function is PRT of that vertex. The span of these three functions is PRT of that edge. The span of these three blue functions is PRT of t. Then, since it's a partition of the set, we obviously have PRT partitions as a direct sum of these spans. This is what we call a geometric decomposition. We've decomposed the finite element space into, or the finite element shape function space at least, into a sum of things, each of which that are indexed by the faces of the simplex. Also, there's some more structure going on here. It's easy to check that PRT of f, if you take the trace on the face of, of that span, you get a bunch of functions on the face, which is exactly the PR, exactly the polynomials of degree r on f that are 0 at the vertices. So the span of these three guys here, the traces of these three guys, their span is all quartics on this face, which vanish on the endpoints. Because I could get all quartics on the face by adding the 2 from here, but I threw those away, and those are the 2 that are non-zero. Okay, and then one more thing that we observe is that that space, all polynomials of degree r that vanish at the endpoints, well, we could divide out by a bubble function, and that would be isomorphic to polynomials of degree r minus d minus 1. Dividing by the bubble function on a d-dimensional face, which is a DMF plus 1-dimensional guy. Okay, so it turns out that this structure can be carried over to PR minus lambda k and PR lambda k. So I'm only going to talk about the PR minus one. PR minus lambda k on a simplex T has a geometric decomposition into PR minus 1 lambda k where TF, so a subspace associated with F, sort of the span of the basis functions will associate to F, only for the F's whose dimension is k or greater. So for 0 forms everything, but 1 forms only edges and greater and so forth. And that space, PR minus lambda k TF, if you take the trace of it, gives you PR minus 0 lambda k on F. Just like here. And then there's an operation which is a little complicated to describe, which is sort of the analog of dividing out by the bubble function that makes this isomorphic to this space. And now you notice when we go from here to here, we lose the minus. Which is good, because we know that the degrees of freedom for PR minus lambda k associated with a face are parameterized by these guys. These are the weighting functions we used. So this has the right dimension. Anything else would be wrong. Okay, got that? This is why I didn't get any sleep last night. So now, how about getting a basis out of this? So now the idea, is to give a basis for each of these pieces, so that we have a basis that's each basis function is either associated with a vertex or an edge or a triangle and so forth. To give a basis for these guys, well, that'll be sort of like a basis for this space here, since they're isomorphic. Now there's definitely going to be a headache. There is a headache coming. Because let's take the simplest case, where r plus k minus dim f minus 1 is 0, constants. Then I need to have a basis for, let's do the case of where dim f minus k is 1. Suppose I want a basis for constant 1 forms on a simplex of some dimension. It doesn't matter. Two-dimensional simplex. In other words, alt 1 in 2 dimensions. So of R2, basically. Okay, I want to have a basis for alt 1 of R2. What's the dimension of alt 1 of R2? 2, right? A common basis is dx1, dx2. But I don't like that basis because that depends on the choice of coordinates. We're trying to use barycentric coordinates. So I have 3 possible barycentric coordinates, d lambda 0, d lambda 1, and d lambda 2. Of course, they're not linearly independent. Their sum is equal to d of lambda 0 plus lambda 1 plus lambda 2, which is d of 1, which is 0. So the natural barycentric basis for alt 1 would be d lambda 0, d lambda 1, d lambda 2, and you pick any 2 of them. Doesn't matter which 2 you pick. The other one is just a sum of the other 2. But which 2 do you pick? Well, I don't know. Smallest, the biggest? Use your birthday? Well, you just have to make some choice. So there is going to be an arbitrary choice. I don't know any way to get around that. So there's going to be some arbitrary choices around here. So that's in the nature of this space, and it's also the nature of this space. So the basis is going to have some arbitrary choices, and we try to get it as systematic and unarbitrary as possible. We didn't use our birthday. So here's what we do. We take, I'm going to create a bunch of basis functions, then I'm going to associate them with edges. The basis function I'm writing down, even though it has an f on it, may not be associated with the face f. You take one of the Whitney k-forms, any basic Whitney k-form, which just means that f is any k-dimensional face of T, and then we know how to define this. This belongs to, is a basis element of P1 minus lambda k. Then you multiply them, since we're trying to get PR lambda k, we multiply it by lambda to the alpha. Lambda 0 to the alpha 0 through lambda n alpha n. And since we want to get something in PR minus, that should be between PR minus 1 and PR. This is between 0 and 1, so this should be degree r minus 1. So we should have alpha is equal to r minus 1. So it's easy check that this thing is in PR minus lambda k. And it's an easy check that, so now we take the set of all of these things. Where alpha is in this and f is a face. And this set spans. So I'll erase this, and I'll just say that this set spans PR minus lambda k. So it's easy to write down a spanning set that's somehow very natural. You take the basic Whitney forms, and to get higher degree Whitney forms, you multiply them by polynomials. So you multiply them by, and you write those polynomials in barycentric coordinates. So everything is in barycentric coordinates. Say for 0 forms, the phi f's are just one more barycentric coordinate. So this is just a polynomial of degree r in barycentric coordinates, as it should be. Okay, but for 1 forms, this would be, you know, lambda sigma 1, d lambda sigma 2 minus lambda sigma 2, d lambda sigma 1. and that gets multiplied by some more monomials in lambda, and that's your basic form. And that form ensures that it's in PR minus lambda k, and they span PR minus lambda k. Okay, but they're not linearly independent. And we can easily see that because of this little identity I put up here. Remember what this phi is. This phi is a sum of you wedge together all the d lambdas, but then you leave out one of it and turn it into a lambda, right? That's the phi. And so you leave out one of these guys and it becomes a lambda in front. Now stick it into this formula here. Then what you'll have is the sum of these where you have two lambdas in front. Lambda sigma I and lambda sigma j, and it'll be a double sum. And so every term will come in twice, but with opposite signs, and they cancel. What's left over is just the volume form, so it's the same after you pull out one of the lambdas. Okay, so we need to get a linearly independent spanning set. And I guess one other thing, which is called a basis, one other thing I should have pointed out, I want to associate this with a face. What face do I associate it with? Well, not with just the face F determined by the vertex indices sigma 0 through sigma k, but also take into account any lambdas that show up here with a power other than 0. So, for example, if we have lambda 3 squared times phi 1, 2, this involves 3 vertices, 1, 2, and 3. So I'd associate this with the face 1, 2, 3. Okay, now what do I do to get a linearly independent spanning set so it's not so it's a basis? Which ones do I drop? I have to drop some, and as I tried to convince you, even in the simplest of all situations, there's some arbitrariness. Drop the lowest one, for example. It's basically what we're doing is dropping the lowest ones, the right number we need. So the condition we impose is that every index that shows up at all shows up either in one of the lambdas or in the F or in both. If it only shows up in, the lowest index that shows up is required to show up in the F. So we don't allow this, lambda 1, phi 2, 3, because this is the lowest index and it doesn't show up in the phis. We do allow this, lambda 2, phi 1, 3, because this is the lowest index. We even allow this, lambda 1, phi 1, 3, because now it shows up in 2 places, but the requirement is it has to show up at least in the phi. The other ones are extraneous spanning functions. They're in the linear code. We can prove that these ones that we throw out, this one, we can prove is a linear combination of all the other ones that we don't throw out. And we can show it's linearly independent. Okay, and I think this is the last slide. So here I write down explicitly the basis for PR minus lambda 1 and PR minus lambda 2 on a 3-dimensional simplex. So I don't have 0 forms, so nothing happens on the vertices. For the 1 forms, things happen on the edges, the faces, and the tets. There are basis functions associated with edges, faces, and sometimes tets, depending on the degree. And for PR minus lambda 2, there's no basis functions associated with edges, just faces and tets. So P1 minus lambda 1, we have the Whitney forms. So if it's the edge xi, xj, it's phi ij. P2 minus lambda 1, we take those Whitney forms and we multiply them by monomials of degree 1 in the barycentric coordinates. And since I want to associate it with an edge, it can only involve xi and xj, so I either multiply it by lambda I and lambda j. And here I'm always assuming I is less than j is less than k is less than l. But I don't have to throw any of these out because I and j all appear in the phi. Both appear in the phi. I also get some that have I, j, and k, 3 different indices. So lambda k phi ij and lambda j phi ik, but not lambda I phi j phi k, because then the lowest index would appear in the lambdas but not the phis. So what do we get here? Let's look at the picture in terms of number of degrees of freedom. In the first case, we get 0, 1, 2. We get phi 0, 1 here, phi 1, 2 here, and phi 0, 2 here. And of course, our degrees of freedom are 1 per edge. That's P1 minus lambda 1. If I do P1 2 minus lambda 1, then I get 2 on each edge. And those are lambda 0 phi 0, 1 and lambda 1 phi 0, 1. And I get 2 on each of the other edges. And in the interior, I get 2 also, which are the two things that are written there. And this is the right diagram for the second lowest order Ravier-Thomas space. So we've given the Bernstein basis for the second lowest order Ravier-Thomas space there. And it continues on in a very similar way. So here we have to allow all quadratics that involve I and j multiplying phi ij, so we get these 3 guys on each edge. And then we have to bring in all quadratics multiplying phi ij that bring in just one more vertex. And we have to make sure that the I vertex is always in the phi. So we only do phi ij and phi ik. So we get 6 guys on each face. And then on the tet, we have to use all 4 indices. So it must be lambda k, l, phi ij. Any of these are allowed as long as the I appears in the phi. So we get 3 in the interior. And maybe, I don't know, is it worth going through the 2 forms? Why don't I stop here? For what purposes? I mean, in this talk, I've basically been assuming the domain is a polyhedron so we can triangulate it exactly. When you're doing the continuous theory, if you get away from Lipschitz, then it's very hard to prove a trace theorem, and it's really hard to work. I'm not a guy who works on less than Lipschitz domains, but of course there are experts who do. Do you know any that you want to compute on? What's that? You mean cross brick kind of thing? True? True? I'm not an expert. Yes, I can comment a little bit. So why do we want to use these Bernstein kind of bases? So I said, well, they're explicit. You could just write them down. That's sort of nice. But after all, the Mathematica is available. You could also compute the inverses. So, but people think that they might have better conditioning properties, particularly as the polynomial degree becomes very large. I tried to read the literature on this subject. Maybe do we still have our spline experts around? This is somewhat occurs in the spline literature, and they're asking different questions and different norms and stuff like that. But it's not a clear theorem like the Lagrange basis grows exponentially conditioned number and the Bernstein grows polynomially or something like that. In fact, I think they both grow exponentially in some sense. But it does, I think the Bernstein tends to be better. But also then there are many other bases around in the world where people try to condition them better. In various ways. And what they generally do, they start with some bases they can get their hands on and start fixing it, doing things, improving it locally on each edge and this and that. And the starting point is usually the Bernstein basis. And that's the way we feel on this. This is probably not the answer to your dreams if you're trying to compute with R going to infinity, but maybe it'll help you figure out the right thing to do. I think it's an area where there's plenty of research to be done. In that paper that we wrote, we give references to various people who had various ideas for various purposes. They were trying to get bases with some properties. So I think the way to approach this problem is figure out what properties you need for your application and then start to think about, is it possible to get something that moves in that direction? Clement doesn't commute with D. No, the correction doesn't make it commute with D. The correction makes it a projection. But once you've done one step that doesn't commute with D, I don't know the trick. So then we'll need the Sarkis tricks to make it commute with D again. I don't know any trick like that. The Schoberl trick says if it's not a projection, we can return it to being a projection, but it had to commute with D. So actually, this is an interesting question in the history of finite elements. We love the Clement interpolant, right? I teach it in all my courses. So the problem is the nodal interpolant is not defined on H1, but you can do the Clement interpolant and you get something that has similar properties, is quasi-local, and is defined in H1. Why didn't we say mollify and then do the regular interpolant? That's an alternative procedure. Just as simple, and that's very rarely discussed. It's been around. So Christensen, I give him a lot of credit for this, but he just sort of said, why don't you do this? It wasn't such a brilliant thing, but I don't know. Now, Clement is quasi-local. Well, mollification is quasi-local too. Schoberl's trick makes it global, which people don't like. So people are trying to get a quasi-local interpolant, which has bounded cochain projection. Open question as far as I know. Definitely.
So it tells you what should be an actual basis, but sometimes for Maxwell's elements, you'll get hierarchical basis. Is there anything like that?
So that's a perfect, so the question is, what about hierarchical basis, which actually is used in more than one way, but a typical way that's used is if I compute with the P3 minus spaces, I can reuse those matrices when I compute with the P4 minus spaces, just as some additional basis functions. So that's a typical example of where people start with the Bernstein basis and then modify it to make a hierarchical basis out of it. If you start with the nodal basis, it's sort of, you can get the nodal basis at level 0, but right at the next level, you're not nodal anymore.